Okay, there is a new homework. I'll show that to you. This is our last homework. So, don't do it too quickly. Make it last. Savor it. So the homework 6 is all about predictive, that's all classification. The stuff we've been talking about and we'll continue talking about for a few more lectures. And my solutions to homework 5 are up on eCampus as well. So here's homework 6. It's due Monday the 25th. And the data you'll play with are some new data that I just now put on eCampus. These are simulated data. But we'll treat them like omics data. So the data set, if you download it, is 2,000 rows and 300 columns. So we have 2,000 features and 300 samples or individuals. And the data were simulated such that there are 3 groups. There's 3 classes. So that could be tumor class A, tumor class B, tumor class C. In tumor class A, the different classes have different mean profiles across the 2,000 features. I forced there to be differences in means that were specific to Class A for some of them, and then differences in means for Class B and Class C. So there are differences between these classes. There is discriminatory information in the data. But not every single feature is informative. Some of them, you find out at the end of this assignment, have nothing at all to do with class membership. So there is a subset of the features that are informative, that are useful, predictive for doing a classification. There's some that are only going to hurt because they're just noise. Okay. We have 300 observations, and the first 225 are your training data. Use them like training data. So these are the data, the samples, the columns that you're going to use to build your predictive models. Remember, we talked in the last couple of lectures about the difference between like a misclassification rate, an error rate, that you compute on the training data itself. So you have your training data. These are omics data for which you know class membership. You use those observations and the class memberships to build a model that will say, just show me the rows of your matrix. Just show me the input variables, not the class membership, and I'll predict class membership. But remember that if we use the training data to build the model and then turn around and apply the model to the same data, the training data, we're going to get an optimistic, an overly optimistic picture of how accurate the model is. Because the model is going to fit the training data better, it's going to tend to treat the training data better than any other sample that you might pull from the same population. To more appropriately assess the accuracy of the method, what we prefer is to have test data, which are observations for which we know class membership, but they were not used in fitting the model. We're going to use the training data to fit the model, but to assess it, to assign an accuracy to it, we're going to apply it to the test data. How many errors did we make in the test data? That's my estimated error rate. Your first 225 samples are to be used for training. The first 75 are Class A, the next 75 are Class B, and so on. And then the remaining samples, the last 75, are test data, 25 for A, followed by 25 for B, and so on. And then the assignment is to apply several different classification methods that we are going to be learning about in the next couple of lectures. K-nearest neighbors, we talked briefly about that last time. So try K-nearest neighbors. That's one method. Try what is essentially logistic regression with a fancy variable selection trick boiled in. It's called the lasso. Try that. Try random forest. This is a tree-based method. It's not a linear model. It's not. It's pretty different from the other techniques, and it often does very well. There's a function. There's a package in R and a function that will do random forest classifiers for you. So try that. Try a simple method, very simple method, probably too simple in most cases, called naive Bayes. And okay. So big picture, you're going to apply several different techniques. This will take a while, so this is your last assignment, but it is a little bit long. It's longer than the last one, that's for sure, the previous one. So I would not recommend putting it off too long to get started. Some of this is straightforward. Some of this will take a little more time. For example, part 4 here, I'm asking you to do a bootstrap. We've talked about how to do the bootstrap. You'll have to use what we've learned to do a bootstrap. Do a bootstrap to get a confidence interval on something. So specifically, we're going to get a test accuracy. This is the accuracy of our model when applied to the test samples. So suppose that when we apply the model to the test samples, it's 92% accurate. We correctly classified 92% of the test samples. But that's an estimate. The real error rate, or the real accuracy rate, whichever one you want to talk about, you would only be able to calculate it if you applied the model to everybody in the population. We're estimating that parameter. Since it's an estimate, it has a distribution, a sampling distribution. We can put a confidence interval on it. Tell me the test accuracy, your best estimate of your test accuracy, and give me a 95% confidence interval for it. Bootstrap is handy here because we don't know what the standard deviation is of that thing. My estimated test accuracy is just the 92%. That's what I got when I applied the method to the test data. But this standard error, I don't have an estimate for it. Bootstrap is a way to approximate, it is a way that you can use to approximate standard errors. And if you have a standard error and an estimate, you can construct a rough confidence interval. Estimate plus or minus 2 times standard error is an approximate 95% confidence interval. What else do I need to comment on? Part D will be a little challenging. Okay, so part D, classify with naive Bayes. Naive Bayes we'll talk about. It's a very simple idea. Doesn't make many assumptions. Well, actually it makes some key assumptions. Let's see. We're going to also do, though, on top of doing naive Bayes, we're going to do feature selection. Feature selection is the idea that we have thousands of features. In our case, in the omics case, we have thousands of genes or proteins or SNPs. And we want to predict some class membership. Do you have cancer or don't you, in terms of the thousands of SNPs that we're going to genotype for you? Chances are I could predict pretty accurately with a subset of the million SNPs on the assay. Can I find a subset of the million SNPs that is highly accurate? It'd be nice if we could boil down to 50 SNPs and say with these 50 SNPs we actually predict with high accuracy, higher accuracy than with all of them, because a lot of them probably are just contributing noise to the model. Feature selection is the process of trying to pick out of the million SNPs, find 50, the best 50. So you are going to do that, and you're going to do it kind of manually. So let's see. We're going to consider different feature set sizes. This is another kind of issue. Suppose we have 1 million SNPs that we're going to genotype for each individual. And we think that perhaps there's a subset of the SNPs that is sufficient and maybe even optimal. What size of that subset do I want to target? Is the sufficient number 100 SNPs or 300 or what? What I want you to do in this problem is consider a variety of feature set sizes, and for each of them, the optimal feature set. Consider using 300 of your features. These data have just 2,000. They're simulated data with 2,000 features. Consider 300. Let's go find the top 300 features. To rank the features, how would you find the top features? Okay, so we have class membership, say, A, B, or C. A feature is interesting to me for this topic if it is different between the classes. If A, B, and C, all three classes have the same average value for feature 1, feature 1 is not contributing much to my ability to discriminate. So in order to kind of rank the features, a sensible thing to do would be to compute some sort of statistic that quantifies how different feature I is between the three groups. We have three groups. Let's think up a statistic, a number we can compute from our data that will be big in magnitude if it's an informative feature and small in magnitude otherwise. One natural statistic would be an F statistic. Think of this like ANOVA. I have three groups, and I want to compare the mean of feature I between the three groups. That's an ANOVA problem. ANOVA is driven by an F statistic. You compute this F statistic that's a measure of the variation between the groups compared to the variation within the groups. We could compute that. I'm asking you to compute something similar. It'll do similar things, but it's easy to compute, and it might as well do this. What we're going to do, we have three groups. I could use t-tests. I could, for feature I, compute a t-test t-statistic comparing class A to class B. And I could compute another t-statistic comparing A to C, and one more comparing B to C. If the t-statistic for A to B for feature I is big, maybe it's minus 2.5, that's big in magnitude. T-statistics, if they're big extreme in either direction, are unusual. So suppose we have a big number for comparing A to B. Then in at least one sense, this feature is informative. If nothing else, it will help me to discriminate between A and B. An ideal feature would be different between A and B, different between A and C, different between B and C. As in, this feature tells me about discriminating everybody from everybody. It's a very informative feature. But I would also be interested in feature I even if it didn't discriminate, say, B from C, if it did help me with A and B, let's include it. Hopefully, by doing this, we're going to get some features that will help us with A and B, some that will help us discriminating A from C, and some that will help discriminating B and C. Some might do double duty in multiple categories, but hopefully there are some in each category. For every single feature, compute these three two-sample t-statistics. A to B, A to C, B and C, and then take the maximum absolute value of those three numbers. Once you've done that, every feature, each of the 2,000 features has a number, a statistic, and it's been absolute valued. So the bigger it is, just the bigger it is, the further away from zero it is, the greater the informativeness of that feature, the greater the discriminatory information that feature contains. So the higher the preference should be for that feature. If we're trying to pick good features, I want that one. Compute that statistic for all the 2,000 features, and then you can order them. In order of discriminatory information, here's the best features. So now if we want a subset of size 300, take the top 300. Out of your 2,000 features, you ranked them in terms of how informative they are. Take the top 300. Okay, another issue, and maybe I'll leave some of this for us to lecture on, but another issue is that process of feature selection, which is very common in predictive modeling, you have more variables than chances are you need. So you try to boil down to the most informative features. And let me just reiterate, oftentimes by boiling down, you're not just simplifying the problem. It's not like the computer can't run because you have too many variables, although that can happen. Really what you're hoping for is to actually increase the accuracy by simplifying the model. And that goes back to the idea that suppose we have 1 million SNPs, but only 20% of them have anything at all to do with the disease we're studying. Then 80% of them are just noise. They're not going to help. So if you include variables like in a regression model that are totally irrelevant to the response, all you're doing is adding to the variability. You're hurting yourself. You're having to estimate extra parameters. You're adding in noise to your model. Okay. So how do you pick the feature set size, though? You're going to consider a variety of sizes, 1, 2, up to 300. For each one of those, you need some kind of measure of, like a reliable measure, a generalizable measure of the accuracy. In particular, you don't just want training data accuracy. Going back to that issue of testing and training, if you were to say, let's try feature set size 1 and 2 and ... 300, and for each one of those, you went and applied it back to the training data, you're every time going to pick the model with more features, because a model is only going to get better fitting to the data you're using if you include more variables. You will overfit. You will eventually perfectly fit the training data if you keep including variables. So you don't want training accuracy, you want test accuracy. We're going to learn this trick that's widely used in practice to approximate test accuracy without test data. Cross-validation is a resampling technique that you apply to training data, and it allows you to estimate a generalizable accuracy, the one that we care about. So I want you to apply this cross-validation technique to pick the feature set size. What that means is for each of these feature set sizes, you're going to pick the top so many, apply or build the model, naive Bayes model, using that many features, but then you're going to use cross-validation to score that model or to give it an accuracy estimate. Use those cross-validation based accuracy estimates to pick. The optimal feature set size, according to my analysis, was 82, with a cross-validation based accuracy of 91% or something. Okay, so the fun part of this one is that it will take hours to run, because you're going to have a couple of loops going on. You're going to loop over the feature set sizes from 1 up to 300, And inside the feature set sizes, you have to use cross-validation to estimate the accuracy. Cross-validation is a resampling technique, like Bootstrap. We're going to resample from the training data with a trick, apply the model. Do it again, do it again, do it again. So there will be lots of looping going on. As we go forward, I will give you some tips on how to make this efficient. It's not particularly complicated to code. This is not a complicated problem. It's just some loops. But there are ways that you can be more efficient in R. One thing you can do in R that's pretty handy if you're going to do much more in R, in particular with big data sets, is to learn how to run batch programs in R. What that means is you submit the program to run on your computer or on a server. Like in our department, we have Linux servers that people run their computationally intensive stuff on. It would kill my computer, so I send it to the server. I run a command in batch mode. That means the processor is working for me, but I don't have, there's nothing visibly going on with the computer. So if I'm on my laptop and I want to be able to submit a command to run for a while, but I don't want to have to sit here and keep the screen saver from coming on, for example, I can close my computer, I can go off and do whatever. And in the background, that processor is still running on my computer. There's a batch mechanism for R. You might want to try that. Another thing that I don't recommend you try on this one, but I know at least one of you is interested or has this would be relevant to you. There's a way in R to communicate with other programming languages like C, C++, and several others, Java. C, C++ are orders of magnitude faster than R on things like loops. R is not built to do looping. So if you have big data sets and you need to do some computationally intensive stuff that's not all that complicated to code, like here this is just let's loop and compute some simple things, I could write that in C or C++ without too much trouble. And that would run, if this takes hours to run, if I could write that little C program, it would take minutes to run. And the nice thing is that in R, you can work in R and load in your data, do your plots and all that, data manipulation, and then from R, you call a special function that spits out the data to C, and then C does everything. So you can have basically an R-looking function that runs with the speed of C. Big data with R is a tricky thing. R is really not optimal for really big data. I'm also teaching in Houston each Tuesday this semester for like an executive MBA crowd, and they're interested in business analytics. So they want to do predictive modeling a lot in a business setting where you have big data. And big data in that setting means millions and millions and millions, potentially, of features. And R gets beat by SAS in some instances. SAS is better at dealing with enormous data sets because R tries to load the data into its memory. R does load its data into its memory. So there's a memory bottleneck. That said, there are some neat tools out there. Have you guys heard of Hadoop? Hadoop? Yeah? Okay. Hadoop and some other software solutions allow you to work with big data in a very natural way. And there are tools like that coming out that interface with R. So long story short, it's getting to where data size is not so much of a limitation in R. All right, so I spent a lot of time talking about the homework assignment, but that's okay. It's a good homework assignment. It'll take some time. The last part, let me just comment here. Of the 75, no wait, we have 2,000 features. Okay, so the first 50 features, if you look at the data, you'll see this just by making simple plots and stuff. the first 50 features are different in A compared to B and C. The means are different in A compared to B and C. So those features characterize class A. Those are like indicators for class A. The next 50 are for class B, and the next 50 are for class C. Okay. Everything else, the mean is exactly the same, A, B, and C. There is no information in these features for discriminating between A, B, and C. And, okay, so then I just ask you to factor that information into your interpretation of results. So given what you now know about the structure of the data, what can you say about how well those methods above did? And in particular, what proportion of those noise features were used by the different methods that you tried? Ideally, you would filter out noise features. Okay. So with the time we have left today, let's move forward and talk about Chapter 4 in the Introduction to Statistical Learning book. Chapter 3 we're skipping. It's linear regression, and I'm assuming that you are comfortable with linear regression. If you're not, read that chapter. It's pretty straightforward, the way it's written at least. So that would be for numerical response variables. You're trying to predict a quantitative variable like PSA level or blood pressure or IQ. Chapter 4 is classification, where we have a categorical response variable. So I'm downloading Chapter 4. Okay, qualitative or quantitative response now. And the classification idea is given your input variables, I want to predict which class you're in. And one thing that would be nice is if instead of just saying you are class A, period, we could say I estimate the probability that you're class A as 0.78, which means the probability you're not class A is 0.22. So it'd be nice if we could kind of qualify our predictions with a probability. Some methods are better at that than others. So they use a motivating example where the response variable is default or not on a credit card. So yes or no, is a customer going to default? Input variables might be what's their current balance and what's their income. Tell me these inputs, I will predict whether you are yes or no default. By the way, if you look at, this would be data like ours where we have two features. We're saying our genes, SNPs, proteins, those are our features or our variables. In this case, we would have two variables, two quantitative variables, balance and income. And on the right, those two box plots, two box plot panels, show us for the two variables individually, are they informative? Are they discriminatory? This is what I'm talking about when I say, are they informative? Balance is, income isn't. The reason that is because with balance, there's a big difference in average balance. There's a difference in what balance tends to look like for people who default versus people who don't. So income, there is some difference, but it's not nearly as strong. I would say balance is highly informative, income not as strongly. All right. Why not linear regression? We've addressed this a little bit already because in the GWAS setting we talked about logistic regression. Logistic regression is regression, linear regression, where the response has been treated specially because it's categorical. In particular, it's binary. Could we not just do linear regression in a two-class problem like this? If we said cancer is 1, healthy is 0. Why shouldn't I just do linear regression of, so linear regression, we usually think of continuous predictor variable or covariate, continuous response. And then we see an observed data set and we say there's a line underlying that relationship. That's what I want to estimate. Suppose we have cancer versus normal. Y is 0 for normal, 1 for cancer. And now we have some variable that might be gene abundance from a microarray. Now we have something that it doesn't make as good a sense to fit a line to. If you fit a line to that, you will, in some sense, capture its essence, but it's just not the optimal solution. Because, for example, we could estimate y, we could have fitted values of y that are not 0 or 1. We could have values of y that are less than 0. So with a categorical variable, doing this is not what you really want. Instead, we do this logistic regression, the logit of the probability of cancer, which is the log odds of the probability of cancer, equals linear model. We could do beta 0 plus beta 1 x. That's what this slide is saying here. Pictures like we just made. Linear regression fit to a 0-1 problem on the left. Logistic regression fit on the right. And it turned those probabilities on the left. If you treat 0-1 as your response, you're modeling the response with a line. Whereas probabilities, they can't be 0 and they can't be bigger than 1. So a more natural functional form, instead of a line, would be an S-shaped curve like this one. One that tails off towards 0 to the left and tails off towards 1 to the right. That's what logistic regression does. When you log transform the probability, you get a logistic curve, an S-shaped curve. I won't go through these because we've kind of talked about it already, but starting slide 6 is some detail on logistic regression. Logistic regression is, a natural place to start this discussion. We're trying to classify. Are you this or are you that? Cancer or normal? That is a logistic regression question. So why not just do logistic regression? Why do we need to learn about linear discriminant analysis and random forests and all that stuff? Short story is, there's nothing wrong with logistic regression, and it often does very well. If you have two possible values, cancer versus normal, absolutely logistic regression is a great choice. A nice thing about logistic regression is that it accommodates both numerical and qualitative and quantitative input variables. Some of the methods we're going to see don't. So in your spreadsheet, you have all your covariates, which are SNPs and genes, but you might also have some other things like age, gender, race that you'd like to adjust for. Logistic regression is a bona fide regression model technique. It is for 0-1, although it is not that hard to access an extended version of logistic regression that's applicable to multi-class, not just 2. There's R functions for doing that. So strictly speaking, this classification exercise could be done at this point because you could just do multi-class logistic regression every time. You can beat that, but if you know logistic regression, in principle, you can go do predictive modeling. You can do classification. I'm skipping some things that I don't care that you worry about right now. Lots on logistic regression. Okay. Starting slide 19. Well, it says slide 19. This one says slide 29, so whatever. Is a different tack to this problem. Now we're going to kind of formally approach this classification problem from a statistical modeling point of view. What we would really like to do, here comes somebody into the clinic, we would like to say, give me a drop of blood, let me run a little assay. I will give you not just you have cancer or you don't. I would like to give you my estimated probability that you have cancer is 87%. A probability would be wonderful. The probability that you are cancer is this, probability you are healthy is that. If we make that our target, some nice methods will materialize for us. So in particular, the authors here refer to Bayes' theorem. Okay, so Stat 101 reminds us that if we have class membership, call it Y, so this could be cancer or normal, or tumor type A, B, or C, and we have some input variables, or let's just say one input variable. So cancer, yes or no. X is prostate-specific antigen number, biomarker for prostate cancer. So predictor. What is natural to do is to say, what's the distribution of X for the different classes? That's totally doable. What is the distribution of PSA for people with prostate cancer? And what's the distribution of PSA for people without prostate cancer? Suppose we said that X for prostate cancer was normally distributed with some mean and some variance. And suppose we said that PSA for healthy people, or at least not prostate cancer people, is also normal. It has a different mean, and for simplicity, let's just say they have the same variance. Then what I would like to be able to say is, what's the probability that you have prostate cancer given your PSA level? What I observe, I'm going to observe data on the X's. I'm going to assume they come from some probability distribution. And what I get to do by applying this thing called Bayes' theorem, or Bayes' rule, is write this quantity that I would like to be able to estimate in terms of things that I can estimate. So in particular, the Bayes rule says that this conditional probability of class membership 1 given your input variable is equal to the probability of your input variable given class membership times what's called a prior probability of cancer. Of all the people, of all the adult males in the U.S., what proportion have prostate cancer? Then before I even meet you, I'm going to estimate, my best guess at whether you have it is that number. Prior probability is what it's called, divided by, I'm just going to say a constant that we don't need to write down right now. But fx given y, that's the normal distribution that we wrote down. We're assuming a normal distribution. Pi 1 is something I can look up on nature.com. What's the, or cdc.gov or something. What's the proportion of people with prostate cancer in the U.S.? If I have those things, I can plug them together, apply this very important relationship, and now I have estimates. I can estimate the probability that you have prostate cancer. Bayes' theorem allows us to flip things around, whereas we observe data conditional on, we allow for the data to differ by class membership. So we observe data, but what we want is to flip around the conditioning. That's what Bayes' theorem is for. This is what I wrote down on the whiteboard. This is the formal relationship. So the constant in the denominator was this thing, but it is, this was to be called a posterior probability, as in we started with a prior probability of cancer, then we looked at your data, and now we have a posterior probability of cancer given data. Is written as a prior times what we call a likelihood, which is the basic what we wrote down when we said normal distribution. All right. Almost out of time. Let me try to tie this. Let me try to get away from the math and show us something intuitive. A very basic idea of classification. If we are comfortable with saying a probability distribution, postulating a probability distribution, like normal. Suppose that PSA is normal for cancer and for control, just with different means. Then that would translate to a picture like this. And what would be my best guess? How should I classify? You tell me your PSA level. Which class am I going to pick for you? Well, if this is the distribution that we estimated for PSA among prostate cancer people, and that's the distribution for healthy people, green is not cancer, red is cancer, say. Suppose you show me a PSA of 2. A standardized PSA score of 2. The density, there's more probability for the red curve sitting over 2 than there is for the green curve. There's more likelihood that it came from cancer than it did from normal. The density height becomes our mechanism for classification. Are you more likely under this class, or are you more likely under that class? So a general idea that we're going to see repeated is that we will classify a new point to the group for whom the estimated density is highest, which is a natural idea. Postulate some distributions, estimate the parameters of the distributions. Now here's a new observation, and you don't know which distribution it came from. Which one does it fit better? Is a 2 more likely to have come from the red one or from the green one? From the red one, because there's more probability mass sitting on top of it. The method that we just kind of described in words gets a special name. Old technique, still widely used, still a good technique, called linear discriminant analysis. Linear discriminant analysis, think normal distributions for my input variables, and I'm going to apply Bayes' rule to get to estimate a conditional probability for each of the classes. And then I will predict or classify each individual to the class for which that estimated probability is biggest. Linear discriminant analysis. So they have some comments about LDA, linear discriminant analysis, LDA, versus logistic regression. I like logistic regression. Logistic regression allows for qualitative variables. Linear discriminant analysis, unless you do something fancy, does not. Because what we have been saying here is normal distributions. We're saying our input variables are continuous numbers and they're normally distributed. So LDA, we'll see, does not accommodate categorical variables. All right, we're about out of time. Let me just preview where we're going. We'll talk about LDA in a little more detail. I'll show you how to do it in R. I'll show you a more general version of LDA called quadratic discriminant analysis, or QDA. Naive Bayes is on this slide. I'll talk about that soon. You don't have to know all these details. There's more in these slides than I expect you guys to get. So, but use the slides, to be reading up. I would recommend on how to do the techniques that are in the homework, because they do show you how to use them. All right. So I will quit there. Are there any questions before I quit there? Okay. All right, and I'll let you go. I will see you Friday.